Okay, so the next one we're going to look at then is seismic surveys. And from this point onwards, they're all ground-based surveys. So they're not remote in any way, so ground-based. So we're starting to see per area cost increase, but we start seeing a more detailed picture of resources and underground features and geology and stuff like that. So seismic surveys are where we use vibrations, and because of the way the vibrations move through the ground, that we call these sound vibrations, and we look for or measure time for the echo to return, and this will show us changes in density, because sound will move faster the more dense it is, and it will also show us sort of boundaries. I'm trying to think of the right word. So things like fissures or cracks and things like this, or tectonic boundaries where you have slip boundaries and stuff like that. So the way that this works is we have our ground surface. We place a sound generator. So this could be a seismic truck with like a thumper that just hits the ground really hard. Or it can be explosives, so vibrations, explosives. And this will send out a wave of sound out into the rocks beneath. Along the surface, we have some what are called geophones. So these are basically like microphones or vibration detectors on the surface that record when a vibration returns to them. So they're all linked up, and they will feed into a control truck or something like that. Repurposed Postman Pat's van or something. There we go. And if we have something that has a change in density, so here we have like an intrusion of igneous rock, or a fissure, or a pocket of oil, which would change density and get all the big petrol companies excited, then the echo would return from that and be picked up by different microphones, and from the time it takes to reach that microphone, you can work out densities and distances. So that's a good one. Covers relatively large area. Next one then, we're zooming in a bit closer, covers less distance. So this again is a ground-based survey. And resistivity is the ability for rocks to resist the movement of electricity. So we measure how difficult how difficult electricity finds it to travel through rocks. So we literally have our surface of the earth. we put a voltage from a battery or something like that. Probably wouldn't be a battery, it'd be like a big capacitor or something, into the ground, and it sends out electricity. Let's do that as a lightning bolt, eh? And then we measure the voltage somewhere else, and how much the voltage has decreased with distance tells us the resistance, and this can tell us what sort of rock it is. So in general, sedimentary rocks have less resistance, and this is because they have water in their pores. And that allows the electricity to conduct through it. Igneous rocks have a higher resistance because they have low water content. Okay. Trial drilling then is where we're starting to get very detailed information. But we are starting to see the cost become much higher, so it's very expensive per area sampled. And this is where we literally drill a core using a drilling rig. And these can be extremely large bits of equipment, so very difficult and expensive to move around. You drill down into the Earth's surface. And keep adding like pipes, basically cores, onto your drill bit, and you extract a core of rock that goes as far down as you possibly can. And then you take these cores that you've drilled out and you do some chemical analysis, and you can find out the chemical composition and ore purity from the rock samples. And these could come from our cores that we've done from drilling. It could come from alluvial deposits. So you basically allowed the river to weather away and erode away material, and you can test that, see if it's got any ores that you want in it or any indications of stuff that you want. Okay, so that's going to increase our cost, but it's the only thing that we can do to find out exactly what's down underneath our feet.